Good morning. Thanks to the conference organizers for inviting me to give this lecture. Today we are going to talk about the state of the current quantum communications technology, about imperfections in the implementation, about mistakes you can make in the implementation, and how this affects the security of quantum communications. When we look at the long history of cryptography, we see that the cryptography over more than 2 millennia has been a cycle of inventing ciphers and cracking them. So a cipher was invented and cracked, and another cipher, better cipher, more complicated cipher was invented and cracked again, and better cipher was invented and cracked again. And this cycle has continued through the years, through quite a long time. So one cipher was knocked down, somebody figured a way to break it, and more complicated methods of encryption have been invented. This continues to the day, this unending cat and mouse game. The interesting question is, can we end this cat and mouse game? Can we invent an unbreakable cipher? And in theory, the answer appears to be yes. First, we have one time pad, the cipher which is in principle impossible to break, as proven by Shannon. And later, we got quantum cryptography. Again, the cipher which is in principle impossible to break, the cipher based on the laws of physics. But can we implement quantum cryptography in such a way that the theoretical promise of unbreakability holds? And this is the important question, because do we have the technology, do we have the ingenuity to actually make the technology work and respond to the theoretical promise? The security model of quantum cryptography is a very beautiful thing. It is quite straightforward. It is based, on the one hand, on the laws of physics. So no more mathematical complexity. We have the hard and cold laws of physics, the laws of quantum mechanics, the best physical theory now today. And on the other hand, it is based on the model of equipment, the equipment which Alice and Bob use to implement the quantum communication protocol. So Alice and Bob follow the protocol and they send over quantum states over a communication channel. Here in a quantum channel, if the eavesdropper can do anything permitted by the laws of physics, including using a quantum computer on the quantum states, do the arbitrary quantum measurements. And if Alice and Bob follow this protocol, and we have correctly modeled the equipment that Alice and Bob use in this equipment model, then we can make a third component of the security model, the security proof, the mathematical and logical derivation that is based on those two. And it arrives at a security result. The result says, when Alice and Bob perform the protocol and they measure a certain parameter, from the value of this parameter, they can tell whether the communication has been secure or not. So for example, in the simplest case of BB84 protocol with single photons, you will measure the quantum bit error rate. And if the quantum bit error rate is below 11%, then Alice and Bob can extract a shared secret key. And if it's above, they have no security and they have to start over. The good parts of this security model are the laws of physics and the security proof. We are not trying to break the laws of physics, and we believe our theoreticians, we can verify the security proofs. They seem to be good as long as the foundation is correct. But in the past several years, there have been many discrepancies found between the model of equipment and the actual equipment that Alice and Bob use. The actual equipment is richer and more complicated than the model. The model is necessarily idealized. In the actual equipment, we have component imperfections. So there is no such thing as 90 degrees polarization or 0 degrees polarization, you always get 91.2 degrees or 87.3, for example. So you have imperfections. The protocol to implement, to make the machines work, the machines are quite complicated. They are much more complex than the protocol on paper. The paper description can take 1 or 2 pages, but the machines consist of thousands of components. So sometimes components have unexpected modes of operation that an attacker can exploit. And finally, engineers make mistakes when they implement. And sometimes they make mistakes in good faith. They just don't understand how to implement the system securely. So we need to show them the way. As you see, as Gilles has pointed out in one of my talks, so if Alice sends polarized photons, a sequence of polarized photons, but each photon has slightly different color. So this is the example of imperfection which can be used to read the polarization without measuring the polarization. It just measures the wavelength of the photons and leaks the information about polarization. And by the way, this is one example of the actual vulnerability when you use polarized photons and source which can emit photons of slightly different color depending on polarization. Anyway, so we have this cycle when researchers discover a discrepancy between the model of equipment and the actual equipment. Very often, when we have such discrepancy, we can construct an attack that breaks the security of the protocol based on this discrepancy. So a hack is published, then the developers and manufacturers rush to fix the hack, patch the implementation, and they try to incorporate the newly discovered imperfection into the security model. So sometimes they change equipment to make the imperfection smaller. Sometimes they amend the security proof to reduce the key rate and make the final key sensitive to imperfection. And very often in the process of battling the imperfection, the whole communication scheme is changed. A new protocol is invented, a new protocol that is insensitive to that particular imperfection. And the cycle continues. The idea is that we should find all the important imperfections and arrive at the second generation of quantum communication technology that is difficult to crack. And we are in this process today. This is a partial list, some examples of the recent attacks and vulnerabilities studied by different research groups around the world. I apologize for omissions. I know a few works are not in this list. I just didn't have space on the screen, didn't have time to update. We have seen a couple examples of new attacks in the poster session yesterday, which are not on the list. And you can see that there are different attacks that exploit imperfections in different components, different parts of the QKD system. Most of the attacks have been checked, tested experimentally. In the list, you see at least 3 different commercial systems. So this process happens today. And what I will do in the rest of my talk is to show you some examples of attacks and countermeasures and how we test them. And I will go a little bit deep in the technology to show how the things work. And the only way, I think the only way you can learn about quantum hacking and imperfections is to see examples, because there is no theory behind it. There are tricks and tools and things to notice. So let's see the examples. Okay. One question is the situation that we have many practical vulnerabilities unique to quantum communication? Is this the first time in the history we encounter the situation when imperfections allow us to crack the security of protocol? It seems to be not. So, for example, not far from here is the National Security Administration headquarters, and of course they have many employees and they have a lecture course. A lecture course that has been declassified today. In the lecture course, there is a lecture about attacks on classical communication equipment based on imperfections in that equipment. attacks that happened 70 years ago. And in this lecture, you can see an example of an attack that happened during the World War II. There was a one-time pad, electromechanical equipment, a machine that implemented the one-time pad encryption. And the American cryptanalysts, to their horror, found that somebody in the next building could connect an oscilloscope to the communication line and see the secret information going in, because it was leaking from the machine. The machine was noisy, it had relays, it had motors, parts which ran on high voltage, and it made interference into the communication line and actually leaked the secret information. So they could read 75% of it across the road. And this imperfection was fixed. This lecture has many more examples of such problems occurring in 1940s, 50s, 60s. And from the fact that this part of the lecture course has been declassified, we can already tell that today we don't have this kind of problem in the classical computer communication equipment. Because the computers got smaller and they got smarter. Now, today, if you have a high security communication equipment, you have the cryptographic module that handles the secret information. Between this module and the communication channel, we have a lot of processing going on. Bus, memory, software, repeaters, amplifiers. So before the signal goes to the communication channel, all the traces of the cryptographic processing are virtually erased from what is going on in the communication channel. But in quantum communication, the situation is not such. In quantum communication, given our primitive quantum technology, really rudimentary technology, we have the cryptographic module connected straight to the optical communication line that goes outside. So the eavesdropper can use optical signals, analog optical signals, in this communication line to access components, security critical components directly and exploit their properties, exploit their imperfections. And many of the attacks you will see today are based on this proximity of the cryptographic components that handle sensitive information, the direct connection to the optical communication line. And I don't think the situation will be forever. In the future, we will have a quantum cryptographic module separated from the communication line by same kind of quantum information processing. So in the future, the isolation of the module from the line will be easier. But today, we have this situation, and we have many attacks exploiting it. Let me start showing you examples of attacks. So one attack. So when we first got our hands onto a commercial, the first commercial sample of quantum cryptographic equipment, we decided to start testing it. And one of the things you have in the QKD equipment is a random number generator. So in the protocol, you are supposed to apply random phase choices or random basis choices on the modulator, both sender and receiver equipment. So this modulator is in the receiver equipment, and Bob. So for each quantum bit Bob tries to detect, he chooses one basis or the other. And the random bits for this detection should come from a physical random source. You don't want to use a mathematical random number generator that's predictable, so you want a physical source of randomness. And the commercial equipment uses such source and claims that the source is very good, passes all the statistical tests, and we decided to verify it. So we connected an oscilloscope to the output of the source, we recorded a long sequence, ran the tests, and the sequence passed the tests. It appeared to be random. Next, we connected the oscilloscope to the output of a digital processor that buffers the random numbers and applies them at the right time to the modulator. And here you see one of the oscillograms we have recorded. So each time a photon passes through the modulator either has a pi/2 voltage pulse, so to apply one basis choice, or it doesn't have a pulse, so here it applies 0 volts, and it has another basis choice. Can anybody spot a problem with this recorded random sequence? Anybody sees a problem? Yes, Charles.
It's not random enough.
Not random enough. Okay, so in theory, This is a possible sequence. But when you see, like you go to a casino and you bet in Las Vegas, and you start betting, and each time you bet, you see the ball going into red, 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 more than 10 times into red. So you know, if you bet the next time into red, you have a very high probability of winning, right? And then the next time it switches to black, it goes black, 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 black. Now something is wrong with the wheel. So there was a programming mistake in this FPGA, in the software that buffers the numbers, and the buffer was not buffering the numbers properly. The mistake was promptly fixed by the manufacturer as soon as we told them. But the lesson is, no matter how trivial mistake you make, this can break security. So this is not about quantum components, this is the stupid programming mistake somebody made or overlooked. And it breaks security, because if you know that Alice is much more likely to emit the same quantum state in a row, several times in a row, you can make an attack based on that and break the security of QKD. Another thing to consider. So we have this quantum random number generator, and it's a separate component, it's a closed metal box, and it is supposed to have inside some kind of physical randomness source. So in case of this quantized random number generator in this commercial system, that will be a light source and beam splitter and 2 single photon detectors that click at random and produce or output random stream. So you have to trust that this is so. Because maybe instead of just this, you have a random number generator with an extra memory, and at a preset times, instead of outputting the true randomness from the physical source, it will just output a random pre-recorded chunk of the sequence of which the manufacturer has a copy. And there is nothing you can do on this output to distinguish the situation. It will look just as random to you, because it's a recorded random sequence. But somebody else will know that part of the sequence, and of course, wherever you use the sequence, the communication can be cracked by that part that has the knowledge of this memory. So you have to trust that your component, cryptographic component, has not been Trojan horsed like this. And if you think the QKD scheme, a typical QKD machine, has very many components on whose correct behavior, on the absence of Trojan horses, you have to rely. So if you look inside the commercial QKD equipment, you see the light source, the laser. This is coming from another manufacturer. So the whole equipment is assembled in one country, in this case Switzerland, but the laser is coming from China. The phase modulator is coming from the United States. The variable optical attenuator is coming from Canada. And each component, if it behaves in a certain way incorrectly, can actually break your security without the machines realizing it. And of course, all the electronics, the processors, the ICs, they all come from different countries, Taiwan, Hong Kong, whatever. So not only do you have to trust the manufacturer of this machine, but you also have to trust the entire chain of supply of this manufacturer. Because there are many components that can be compromised if the supplier of that component or this component decides to attack the finished product. And I'm afraid there is nothing you can do about this. To refer to the NSA again, the NSA has their own semiconductor manufacturing plant for exactly the reason that they don't trust the suppliers of ICs from anywhere else. And it is quite difficult to verify. You can X-ray the component to see the X-rays and to see if there's something else inside this component, for example. But if it's just a software modification, you will be hard-pressed to find it. Another example of attack. In a typical QKD scheme, there is more than one single photon detector. So for example, there are many QKD schemes that use 2 single photon detectors. One tries to detect bit ones, and the other tries to detect bit zeros. Why is it fun? Ah?
You just gave us a picture.
Oh, sorry. Yes, so this is bit 1, this is bit 0, okay. I'm sorry. I shall use my thumb and this. Yeah, so we like to give a finger to the builders of QKD schemes. So, if you, what if bit 1 and bit 0 happen at the same time? Sometimes, so this is not supposed to, if you use single photons, in theory, simultaneous click of both detectors does not occur. Because if everything is perfect, there is only one photon, so it always goes to one detector or the other detector. But in practice, sometimes you have two photons, because the source sometimes emits two photons. And they can split each to its own detector, so both detectors click at once. Detectors have dark counts, so sometimes they click without a photon. So occasionally, you will have both detectors clicking at the same time. As an experimentalist, what do you do with those double clicks? They clearly arise because of an imperfection. So the naive, the intuitive idea is just to discard them, disregard. So you only use single clicks in the protocol, but you discard double clicks. What can happen in this case? The if can attack. If can use a copy of Bob's equipment to detect everything coming from Alice. And then she regenerates the measured quantum state according to her measurement, but not as a single photon, but as, say, 100 photons, and sends them over to Bob. In the case that Bob chooses the same basis as if, so Bob makes a random choice of basis, he chooses the basis randomly and independently of if, independently from Alice. Half of the time, he will choose the same basis to if, as if. It just happens randomly, half the time. And in this case, all 100 photons will go to one detector in Bob. Let's make this one. And our detector cannot distinguish one photon from 100 photons. It's non-photon number solving, so it will say I had a photon as bit 1, and it's the same bit if as detected. So fine. And the other half of the cases, Bob will choose a detection basis which is not the same as ifs. And in these cases, approximately 50 photons will go into one detector, and approximately 50 photons will go to another detector, so you have a double click. And we have just agreed to discard those double clicks. In result, what remains in the key are only cases when Bob had the same detection basis as if, and if has a perfect copy of Bob's detected key. So security is broken. The correct treatment for the double clicks or multiple clicks in detectors is, whenever this happens, to make a random choice and record this as a single click detection with a random value. Then this attack doesn't work. Another example of attack. So now we will be talking about a Trojan horse, but not a physical Trojan horse, but a Trojan horse made out of light. So we have a QKD scheme, say Alice, which contains a modulator inside. In this modulator, the modulation values we are very interested in because they contain the secret bit information. We will have if who takes a high power laser and injects a bright pulse, a very bright pulse, into the communication line towards Alice. Literally, large number of photons. So she can make very bright pulse, it can be milliards of photons. And she multiplexes into the line this pulse at a slightly different color, slightly different wavelength, or slightly different time in such a way that this pulse does not interfere with the actual quantum states. The quantum states are transmitted normally from Alice to Bob. It does not measure quantum states. But she just injects an extra bright pulse inside Alice. This pulse will get attenuated, and some part of it will pass through the phase modulator. She will time this pulse so it passes the phase modulator at the same time as the phase modulator is preparing the outgoing quantum state. So this bright pulse will get modulated by the same phase shift. Then, behind the modulator, there are many other optical components, and all components have some finite amount of back reflection. Like when you look through a window from inside to the street, if we treat the window as a perfect component, you are only supposed to see the street. But if you look closely, you will also see a little bit of reflection of yourself. So the same kind of partial back reflection you have from any optical component. And then a small part of this pulse will get back, and as long as Eve has at least one photon going out, she can pick it up and measure this phase, all without interacting with the quantum state. So she will learn the secret bits without introducing any errors in the communication. Of course, she does not interact with the quantum states. So this attack has been experimentally confirmed several times. So Eve can use, for example, a Michelson interferometer that has a reference arm and another arm that goes inside cryptographic module, passes the modulator, and ends with one of the available back reflections from one of the components. So in this interferometer, if you apply voltage at the phase modulator, you see the different interference in this Michelson interferometer. So you can read this modulation voltage. And here you can see the first hacking experiment 16 years ago. So equipment is a bit dated. And this is the reference arm of Eve's interferometer, which is covered in insulation to reduce phase drift. This is a reflectometry measurement to show of a commercial system, plug-and-play commercial system Clavis from ID Quantique that shows many available back reflections of components. So here, the level of back reflection is plotted as a function of the distance from the entrance or time delay from the entrance. And the end of each red bar corresponds to the level of back reflection. So minus 40 dB is 1 over 10,000. 10 to the minus 4, and so on. Minus 60 dB is 1 millionth fraction of back reflection. And you can see that both Alice and Bob, many of the components have, such as connectors, interfaces between the component and fiber, have back reflections of different level. Both Alice and Bob have back reflections. So in Bob, he is the phase modulator, and behind the phase modulator, there are many components that give us back reflection. So this connector gives us minus 50 dB back reflection, and this interface guy makes minus 70 dB back reflection. So you got some reflected photons back after they pass the phase modulator key and the phase modulator key. So let's make a little brainstorming, and let's consider this plug-and-play scheme. And see how we can protect it against this Trojan horse attack. To briefly remind you the plug-and-play QKD scheme, in plug-and-play scheme, the communication begins with Bob's laser emitting a sequence of bright laser pulses. The bright laser pulses split into two arms of interferometer. One of them is rotated by polarization, so they can combine with different polarization. First pulse into pairs of pulses. First pulse has vertical polarization, the second horizontal polarization. They are bright pulses at this point. Bright pulses unmodulated, they don't carry information. As bright pulses, they pass the communication line towards Alice. Alice has an optical attenuator and a mirror, a Faraday mirror that reflects the pulses. And Alice activates her phase modulator to make a phase shift to one of the two pulses in the pair, to make the phase difference between different. At this point, she encodes her quantum state, random basis choice and random bit value choice. Again, the pulses pass the attenuator on the way out, and at this point, they are at a single photon level, and they carry the quantum information of Alice. They go back through the communication line to Bob. Bob splits them into the interferometer, and he the interferer, Bob detects the quantum states with two single photon detectors. This scheme is more vulnerable. I think it's one of the most vulnerable to the Trojan horse attack. And here we have both Alice's modulator that carries secret information, and we have Bob's phase modulator in one of the two protocols used by the system, in SARG-04 protocol. This phase modulator also carries secret bits, secret information. How do we protect this phase modulator and dot phase modulator against the Trojan horse attack, against the eavesdropper interrogating them by bright pulses coming from the communication line and reflected back, coming from the communication line and reflected back? Ideas. I will take a few suggestions. What countermeasures are suitable to Trojan horse attack in this scheme? Yes, one per suggestion.
So a monitor, so something that's looking for incoming light, measuring, looking for bright pulses.
Okay, so you have a monitor that is looking for the bright pulses coming from the light. something like a photo detector, right? Good. More suggestions? Yes? Okay, can we use an isolator? So we can put an isolator that passes the pulse in one direction, but not the other. Okay? Another suggestion? More. Okay, the isolator will not work because it will also stop the communicating leg between Alice and Bob. This is a double pass, back and forth. So if you use the isolator, you will stop your communication as well. Other ideas? Hey, give me silly suggestions. I'll give you 30 seconds to come up with ideas. 3 more ideas, and we will see what the manufacturer has done. Think, discuss between yourself. What? Change protocol. What protocol do you suggest as a replacement? One-way scheme. Okay, yeah, maybe. Ah? Oh, the first word you said?
Make 2 copies and use each in only one direction. So put an isolator in each one.
Okay, so change the protocol to one-way protocol and then use isolators. Yeah, okay, good. More suggestions? Put a filter. What kind of filter? Okay, to put a filter on the entrance, so only one wavelength passes. So if is forced to use that wavelength. Okay, more suggestions?
Yeah.
Yes.
To put a time filter that lets light pass through exactly at the time that you expect it to be there.
Okay, so wavelength filter and time filter. Like a modulator which opens only at the exact time. Okay, good. More? Hey, guys. Yeah, yes, Sharon.
I don't trust circulators or isolators because they're not perfect. So you can defeat them with very bright pulses, but perhaps a rotating wheel with teeth would really stop the pulse.
Okay, so let's make the, okay, Charles Bannon's suggestions, he doesn't trust purely optical components, so let's make the time selection switch mechanical with a rotating wheel with rotating holes. Rotating wheel with holes. Good. So you can make it mechanical, so it's more understandable. Yeah, yes?
So Bob can use very short pulses, vary what time they appear with no more repetition on the load with his own pattern, and then they can exchange that pattern over the class of the channel, and if the pulses came in, or other pulses came in at another time, you know that it was the
Okay, so if I understand the suggestion is that Bob does not make a continuous sequence, but varies the timing of each pulse in the sequence according to a predetermined, pre-shared pattern, and then detects the time exactly in Alice or I don't know in Bob, and checks if they indeed come at the expected time. And if Eve shoots a pulse at a different time, she will get caught. Good. Let me give you a hint. Do we need to have an active modulator in Alice or in Bob? Are there schemes out there that don't use modulators? Lots of them. You can use entangled pair source that doesn't have a modulator, so you prepare the state passively. And there are different schemes like different kind of distributed phase reference schemes that don't use a modulator in Bob at all. So if you don't have a modulator, you don't have these problems. I'm giving the suggestion myself. Okay. Enough, I think. So we had some good suggestions and some interesting suggestions. But for now, we are stuck with this plug-and-play scheme because the company decided to invest a lot of money to develop the equipment, and they need to make this scheme work and be secure against Trojan horse attack. So ID Quantic did the following countermeasures. ID Quantic in Alice they implemented a pulse energy monitoring suggestion detector. So that's the first suggestion. This is a detector that measures the energy of each incoming pulse. And if the energy is above a certain threshold, it stops communication or raises alarm. In addition, they do have a wavelength filter at the input. The purpose of this filter is to restrict it to using a specific wavelength or a very narrow wavelength range, the wavelength at which the characteristics of this detector and characteristics of other components in ALICE are known. Because if uses a different wavelength, it might be that you have less attenuation or less sensitivity of this guy, and then it can still then do the attack. But the filter restricts it to using one specific wavelength. In Bob ID Quantique, in order to protect eavesdropping on the SARC from eavesdropping in the SARC protocol, they did precisely nothing. No countermeasures. So this was the obvious omission, which we decided to try to exploit. We have Bob, and we want to learn the phase modulation value scheme. We built a scheme when if shoots a bright laser pulse at 1550 nanometers, the same wavelength as the system uses. So if the way I filter it will not help. This bright pulse comes, passes the phase modulator, gets reflected from one of the reflections. So we choose a minus 50 dB reflection at a connector behind the phase modulator, just a bulkhead connector between two optical cables. And back come a few photons, 4 photons. And those 4 photons are modulated by the phase shift. We can read the phase shift by using a kind of Michelson interferometer with photons coming to one arm and a bright local oscillator pulse coming to the other arm. This is so-called Hamadine phase readout scheme. Here, the strong local oscillator interferes with those 2 photons, and the process amplifies the fluctuations in the electrical field. So if you have 2 photodiodes behind and you subtract the photocurrent, you have classical amount of photocurrent that tells you about the phase of those photons. This readout actually works very well, so we could read with high probability the phase shift at this phase modulator. The problem in this experiment was that while 4 photons come back, the remaining 2 million photons hit the single photon detectors. And even though the millions of photons hit them outside of the gate, so the detectors are gated, they are only activated for a short time, and we time this pulse so they get hit outside of the activation time. But still, it's a lot of photons, and they cause formation of some photo-generated charges inside the detectors. The charges get trapped inside deep levels, trap levels inside detectors. And next time the detectors are activated to detect a single photon coming from ALICE, they have an after pulse or random click with a high probability, unfortunately, because Eve has just hit them with a lot of light. And the probability that the random click occurs after a few gates, after just 4 or 5 gates, it's already 50%. So when Eve does the readout, she unfortunately also introduces a very high quantum bit error rate in the transmission, and the transmission stops. Alice and Bob see too many errors in the transmission. So in effect, Eve has only done a denial of service. She stopped the transmission. And this is not a useful outcome for it. What she wants to read the secret information without stopping the protocol. So unfortunately, for this particular commercial agreement, because one component had an imperfection, after pulsing is an imperfection. This imperfection prevented an attack exploiting different imperfections. So for once, ID Quantique got lucky. Of course, the next thing we are trying to use a longer wavelength, so different wavelength, 1924 nanometers, not commonly used. And at this wavelength, the after pulsing probability, so the material of detectors, indium gallium arsenide, gets very transparent on this wavelength, so the actual after pulse probability actually goes down a lot, orders of magnitude. But also the losses in the optics of this wavelength are also higher, so we are now trying to see whether we can improve the attack and actually make it work. So we will see. Yeah, so one of the things Eve can do, she can use a different wavelength to attack this. Now, But this is not confirmed. We have not confirmed whether this will work or not. We still experiment. So ID quantique for now, they don't have countermeasure. Maybe they don't have to. For this pulse energy monitoring detector, this is a classical detector, and this detector is implemented using an electronic socket. So the actual electronic socket to implement pulse energy monitoring consists of a PIN photodiode, so a classical photodiode that receives a fraction of light coming to Alice's input. Then the photocurrent is amplified by an amplifier, then goes to an integrated socket. So this integrated socket changes the voltage at this capacitor proportionally to the voltage at the output of this amplifier. So the change of voltage on this capacitor is proportional to the energy of the light hitting the photodiode within the bit slot. So the integrator is active for the duration of the bit slot. And the idea is that the voltage should integrate the energy of the light coming in. Then there is a comparator. The comparator clicks if the energy of the coming light is above a threshold and makes an alarm signal for the system. It will be easy to say that in this particular implementation of the electronic scheme, so the idea is good. We think the idea is good. Indeed, this is how you would measure the incoming energy. You need to integrate the amount of incoming light, and you need to use some form of integrator, electronic integrator, and then compare the energy of the incoming light with the expected energy, and if it's more than expected, you raise alarm, you stop communication. But the implementation of the electronics, the engineer at ID Quantique has made several mistakes. And it's a very easy thing to say that he has made a mistake, several mistakes that allow us to attack the scheme. But this would not be the whole story. The actual story is we don't have any implementation standard for this kind of detector in a cryptographic equipment. So ID Quantique had to devise to make their own implementation standard. And they developed a standard for implementation and for testing of the scheme. And they said, if the monitoring scheme receives a normal sequence of pulses, like pulses of a well-defined energy that happens in a normal communication, and one of those pulses is very slightly brighter than the rest by 0.1 dB, 0.2 dB, a few percent brighter, then the scheme should make an alarm. So they made this testing standard. ID Quantique has actually implemented the testing rig. So they had the extra laser which injects a little bit extra light, and they calibrate each equipment before they ship it to the customer. They calibrate and they see that it gives the alarm at the proper settings. So when the light is a little bit more, it gives the alarm. So each system is calibrated, shipped to the customer. And they do it in the company. They calibrate this part of the scheme, and it works. But what about the actual implementation? In the implementation, you would expect that this amplifier has enough bandwidth to resolve each individual pulse coming from the line. So you would expect that the voltage is just repeats the shape. But the actual amplifier, for engineering reasons, does not have enough bandwidth. So this is the actual oscillogram at the output of the amplifier. And you see that it does not resolve individual pulses. The pulses are more like little bumps. And if this pulse is brighter, the bump is a little bit brighter, so the scheme actually works. It passes the test successfully. So the company-defined standard says this implementation is okay, because one pulse is brighter, there is alarm. But as a hacker, of course you can do this. You can remove the 3 pulses and make each 4th pulse up to 8 times brighter, and this scheme does not give you alarm. And then, of course, the 8 times brighter pulses give multi-photon output out of Alice, and that you can attack and break the security. So the problem was not the implementation. The problem was an incompletely defined standard or poorly defined testing and implementation standard. So the first lesson we have is we need implementation standards, and we need testing standards, certification standards for different parts of QKD systems, for different parts of quantum communication equipment. And I think we are in the process of getting the necessary implementation standards. So we will get there. I would even say we are almost there. There is a lot of effort in this community to standardize, to come up with standard testing methods. In particular, for many years, the European Telecommunication Standards Institute Industry Specifications Group in QKD has worked to define and publish such open international standards on different aspects of implementations, including security aspects of implementations, for how to implement and how to test components, how to test the systems for security. And for a Trojan horse attack, one of the first things they have done in security, this group has almost finished the development of the implementation standard for one-way QKD system, how to protect against the Trojan horse attack. On Monday, the lecture by Alexander Dixon from Toshiba, you have seen more information about this standard, about the implementation of this protection in a one-way QKD system. And I just remind you that the standard defines how much attenuation and how much isolations and how much bandpass filtering you need. So what should be the characteristics of the number of those components to actually protect from any possible Trojan horse attack against one-way alias encryption. So for one-way QKD, we already have a well-defined standard, and I like this work. It's the right direction. It shows us how to do standards. Now we need similar implementation testing standards for other parts of QKD schemes. So for plug and play, we need similar standards on the pulse energy monitoring equipment. And for other imperfections, other components, we also need similar standards. So maybe I should make a little stop and take questions at this point. I have more material to cover, but you have any questions so far? Yes? We can't hear you.
Hello? Yes. You have just shown that an engineer's hacker can overcome some certification, internal certification of the company. How can you be sure that the certification developed by some authority cannot be overcome by some another approach?
The only method we know for this is wide scrutiny. So the standard should be published, and then the whole world, whomever cares, should try to break it. So it's the same approach we use for classical cryptographic systems. AES, other forms of mathematical cryptography. The standard is published, the implementation is known, and then everybody, whomever cares in the world, tries to break it. And there is no guarantee, so there is no loophole left. You can only have a reasonable guarantee when you say, oh, nobody has managed to find the problem in 10 years. So it must be okay. Yes?
So the attack that you kind of said you couldn't do anything about, the one you had the least hope on, was this internal device that was just recording the key? You know what I'm talking about? Maybe, no, yeah, when you just had the internal device that was recording the key as you go and sending it to some manufacturer. The manufacturer implanted, right?
The physical Trojan
horse.
So
I guess my question is there an analogous problem with conventional cryptographic systems that has this kind of thing? Like, is this a unique problem to QKD, or is this a new problem where?
Of course, every cryptographic system, no matter quantum, classical, pen and paper, whatever, it has this problem. So if the component that performs the protocol has been Trojan horse, has been intentionally compromised, of course, every cryptographic system whatsoever will have this problem.
Yeah, I guess my point is the other ones are kind of physical attacks that are problematic to QKD implementations, but that just seems to be a problem that's just there, right? That QKD can't solve, but it's not unique to it.
Yes, but I want to emphasize that QKD does not solve this kind of problems. It's intrinsic to all cryptography. But QKD has new types of components, so you need to look at the new unique types of components and can be new unique types of attacks, but the general problem is the same. Yes, you need to look for implementation. Charles?
Well, this figure goes well with your recommendation for implementation standards of things that are not specifically cryptographic, but just basic electronics. That, I think, you might agree that you can get some more security by a sort of DIY approach, where important components of the system, you have to build it yourself to be sure it isn't bugged this way. And if you publish directions for how to build it yourself, you're likely to be more secure than if you buy it from several untrusted manufacturers.
Yes, I agree. I think this is the way the bigger countries are going. Like Russia and China, they probably want to use their domestic manufacturers for all components, or at least have the replacement available. Yes. But I also agree with Charles that the standard should be open. I don't know if anybody else agrees.
I would like to follow up on the first question concerning the standard and the definition. Like what you presented seems to be a very descriptive standard, which says you have to implement this and this and this in order to protect against that attack, which seems to me not only descriptive but also very restrictive, since it prohibits like other ways in order to prevent this attack in this way. You know, like for example with the FIP security standard, those kind of standards are very difficult to change and adapt to like problems. My question is, where do you see the advantage of this way of defining standard instead of going the other way and saying the system has to be secure by against certain tests and prevent then, for example, an attack independent of the way it is?
Yeah, if I can comment, I think we can do either way. So you can either do a better test, or you can try to define the good practice implementation. Right? And I don't know which is better. Yeah, so here, of course, here the test is insufficient. So you can try to define better tests. Say, okay, try to remove pulses, try to do other things. Or you can try to say, okay, so this, you have to do a specific implementation that has certain characteristics, and that will be more resistant. I think there was a question in the back.
Hi. So first, I'd like to comment that on your first slide, where you put all those components, electric components between a conventional system, conventional crypto system, that's slightly incorrect because there have been attacks on those systems based on, say, power out, but that's besides the point. I'd like to follow up on Zach's question. What does quantum key distribution actually buy us vis-a-vis security besides some really neat mathematics? This is a proactive question, I suppose, but this is my first time with QCrypt, so I'll ask it. Is it really, I mean, given enough resources, you can break any system. The question is building a system that takes a lot of resources to break. Does quantum key distribution give that to us?
I can comment on this. I think what it buys us is this. So the basis of the security, the basis of the algorithm is the laws of physics. In mathematical cryptography, we have the assumptions of complexity that get broken all the time, and there is no guarantee that somebody does not have the algorithm to break them. But here we have the laws of physics, so the complexity is replaced by the laws of physics. But in terms of implementation, I think it's the same story with classical cryptography and with quantum cryptography. In both types of cryptography, we have implementations, and we have to look for loopholes in implementations. The only selling point of quantum cryptography for me is that it bases the security in principle on the laws of physics. So that part of the foundation is secure. Okay, I think we should go on and you can ask more questions in the end. Let me try to show you more examples of attacks. Okay, one other imperfection, which is a very important imperfection, is a multi-photon light emission from the light source. So, in the original BB84 protocol, you were supposed to use a single photon light source that only emits one photon at a time. But that kind of source, it is possible to build, or it is possible to build a source which comes close to emitting one photon at a time. But those sources are more complicated and more expensive. So it is much more convenient just to take a laser which emits bright pulses, take an attenuator, optical attenuator, and attenuate the mean photon number per pulse to much less than 1. And if you do this, then most of the pulses emitted from such source will be empty, so 0 photons. And with the next highest probability, you will have 1 photon per pulse getting emitted. And you can build a QKD protocol or quantum communication protocol using those single photon pulses. So whenever you have 1 photon, it can be used. But the problem is this kind of source inevitably occasionally emits 2 or more photons in the pulse. And that is a security problem. If both photons are emitted and prepared in the same quantum state, then Eve can take 1 photon, store it in a quantum memory, pass the other photon to Bob without measuring it. She then waits until Bob announces the detection basis, and she measures her stored photon in the same basis, and she learns the bit value. So each multi-photon pulse emitted from the source is a bit leaked to Eve. It was realized around the year 2000 just how bad this problem is in terms of restricting the link distance, restricting the amount of losses you can have in a communication link. In practice, it restricted the length of fiber optic quantum cryptography to something like 20 kilometers, which was quite short. And I must note that in the original 1992 paper by Bennett, Bisset, Brassard, Salveil, and others, this problem was already described. But for those 8 years, the community was busy solving different kinds of technological problems. And only in the year 2000, this was really noticed how bad this multi-photon emission is for security. But then, what is interesting to see are the dates. So, year 2000, it was realized how bad the problem is. And 4 years later, several advanced QKD protocols were proposed. And each of those protocols is immune to this problem. Decoy state protocol, Sargo4 protocol, distributed phase reference protocols. In each protocol, this kind of source that has multi-photon emission can be used securely. This multi-photon emission is inside the security model for that protocol. So nowadays, in most equipment, this kind of source is actually safely used, and the equipment uses one of those protocols. But, of course, you can notice that the introduction of the protocol to solve one problem can sometimes open another problem. So the SARC protocol solves this problem of multi-photon emission. But you have just seen that when you have SARC protocol, you need to protect Bob's phase modulator from eavesdropping. Unlike BB84, where you don't need to protect the source, the modulator and Bob. So you need to be careful. Another example, the last example of imperfection I will give you today is a bunch of imperfections that single photon detectors have. The most practical kind of single photon detectors to use in QKD are based on avalanche photodiodes. To make an avalanche photodiode sensitive to single photon, the avalanche photodiode, or APD, is reverse biased above its breakdown voltage. When it is biased above breakdown, the internal gain is infinite, but if there are no carriers inside the p-n junction, it conducts zero current. Whenever a photon comes, the photon creates an electron-hole pair, and this electron and hole are quickly multiplied to a large number of carriers, and then a macroscopic electrical current flows through the photodiode. This current is detected with a threshold by electronics, and if the current is above the threshold, this is registered as the arrival of the single photon. The electronic circuit then lowers the voltage below breakdown. The avalanche stops because the APD no longer has gain to sustain the avalanche. A short time after, the electronics raises the voltage above breakdown, so it is ready to detect the next photon. Single photon detectors are a delicate and tricky technology. In practice, they have 6 or more different vulnerabilities, different imperfections on which you can build attacks. And I will show you only 2 of those vulnerabilities, but just be aware that there are more. So one obvious vulnerability we can consider is that after detection of the single photon, the photodiode spends some time being insensitive to single photons. When we have a QKD scheme that uses several APDs, several detectors, whenever one of them clicks, this detector remains insensitive to incoming light for that particular encoding, in this case polarization. What if can do? If can mix in the channel a relatively bright pulse, so multi-photon pulse, with a particular polarization. So if she mixes with this horizontal polarization, the pulse will be split between 3 detectors in the system. All 3 will click at the same time, and all 3 will have that time. But one detector of orthogonal polarization will not click, and it will remain sensitive. So if Bob registers a detection in his detection system during this dead time of 3 detectors, it is only possible to detect photons of one polarization. And then if a detection occurred there in this time, it must be dot polarization coming from Alice. So you can attack the system this way. Of course, the countermeasure is to, whenever one detector clicks, you should disregard all detections coming from all 4 detectors, even when the other detectors remain sensitive. So you should only be accepting detections at the time when all 4 detectors are sensitive, but whenever one of them is having that time, do not accept clicks. Seems to be sufficient countermeasure. Another problem, another vulnerability. So when the detector, the APD, is in this linear regime, biased below breakdown, it is not sensitive to single photons, but it is still a photodiode, so it is still sensitive to bright light. If bright light is applied to the APD below breakdown, the APD will conduct photocurrent, and this photocurrent can be mistaken, detected by the electronics as the avalanche photocurrent. So the detector scheme can register a click, and the click threshold becomes a classical threshold on the power of the input light here. If Eve has access to detectors in this linear regime, she can also break security. How would she do this? Let's assume for a second the detectors in Bob are working in such linear regime. I will show you on the next slide how this can be done, but assume that they are in the linear regime. Eve can use a copy of Bob to detect all quantum states coming from Alice. Then she can use a copy of Alice to recreate bright light states according to her detection results and send them over to Bob. Bob, for each qubit coming from the line, Bob makes a random choice of detection bases, independently from Eve, independently from Alice. In one half of the cases, Bob's detection bases will happen to be the same as Eve's bases. In this case, this bright light state interferes inside Bob. Almost all light goes to one single photon detector, and in this detector, it crosses the detection threshold, and this detector always clicks. The other one never clicks. In the other half of the cases, Bob's basis choice will be different from Eve's. In this case, the light does not interfere, it is split evenly between the two detectors, and in both, it stays below the detection threshold. So Bob never has a click there. Notice that in this procedure, after Bob is done with his detections, for those bits that Bob has detected, his bit value and basis choice is always the same as if's. So if has identical copy of the row Bob's key is. What follows in the quantum communication is a classical post-processing protocol. So if Bob and Alice compare the detection bases, half the time Alice's basis does not match Bob's, so they discard the incompatible bases. Then they do error correction, privacy simplification, and arrive at the final secret key. This classical post-processing communication in the protocol is not encrypted. It does not need to be encrypted. So if can listen to this communication, just passively listen, and do the same operations to her copy of the key. And because she has started with the same key as Bob, she will arrive at the same secret key as Alice and Bob and Eve. They will all have the same secret key. And this attack does not introduce any errors in the transmission. Can we see it? So the security is broken. If we can get detectors working in a linear regime, how can we make the detectors work in a linear regime? Take gated single photon detectors. The gated single photon detectors in a QKD system are actually spending most of their time in the linear regime. So they are biased below breakdown, and then only before a photon is expected to arrive, the voltage is raised above breakdown for a short time. This is done to reduce noise in detectors. So they are actually in the linear regime most of the time. Eve can blind them completely to single photons by just shining a bright light at the detector. So continuous wave bright light, continuous wave laser. What happens in the detector? The APD conducts photocurrent continuously when it receives light. In all detectors, there is some form of electrical impedance between the high voltage source and the APD. So this continuous light produces constant photocurrent. This photocurrent causes a voltage drop across the bias impedance, and the voltage at the APD drops below breakdown, even inside the gates. This detector is blind to single photons. But if Eve additionally applies a bright light pulse, this bright light pulse will cause clicks in the detectors with a controllable threshold. Here we can see oscillograms from the commercial QKD system. The detectors are blinded with 1 milliwatt continuous wave power. In addition, Eve applies 650 microwatt pulse, which never causes clicks, but if this power of pulse becomes slightly bigger, it always causes clicks. So the detectors are controllable, and this will break the security unless the system implements some kind of countermeasure against this. Yes? To implement this attack, to steal the secret key in this attack, Eve will need a copy of Bob's equipment and copy of Alice's equipment. The detection basis and detection result of Bob's copy of Bob's equipment becomes the input basis and input bit for Eve's copy of Alice's equipment. She will need to make the light sent from Alice's equipment brighter, so the detectors in Bob get controllable clicks. She can use an optical amplifier, or she can reuse attenuation inside Alice's equipment. In addition, she needs a continuous wave laser to blind Bob. In this kind of scheme, by the way, so when Eve does intercept resend, so this attack amounts to intercept resend. She detects every Alice's state and then transmits classical information and recreates the state from the classical information. In this type of attack, you can never have security in QKD because it has been shown that this attack, intercept resend attack, breaks entanglement between Alice and Bob. So no entanglement can be distributed to intercept resend channel. So if you can implement an intercept resend attack, then by definition you cannot have secure QKD. This intercept resend scheme has been implemented on a complete QKD system, research QKD system, in the National University of Singapore. So 300 meters of fiber between Alice and Bob, and in this experiment, the actual eavesdropper that does intercept and then resend as bright states has been implemented, built, implemented, inserted into the communication line. And in this experiment, Alice and Bob run the QKD protocol, and the key parameters of the protocol, such as the key generation rate, the quantum bit error rate, did not change significantly after the insertion of the eavesdropper. So it all looked normal to Alice and Bob. So and this, by the way, is the most complete eavesdropping experiment to the date, still remains, so to my knowledge. Countermeasures against detector vulnerabilities. There have been many proposals of countermeasures, and most of them center around making some monitoring of electrical parameters inside the detector. So if uses bright light and there is a big photocurrent through the detector, you can think of measuring this photocurrent or measuring other parameters of detectors. So most proposals try to make detectors with extra monitoring sockets, extra tricks inside the detector. But as I said, there are several different vulnerabilities associated with the detector. And actually, the construction of that kind of countermeasure turned out to be very tricky. You can close one attack, or maybe two attacks, maybe three attacks, but not all of them at once. So some years ago, a better proposal came about. The proposal modifies the QKD scheme very heavily in such a way that the detectors are no longer inside the secure equipment. The scheme is called Measurement Device Independent QKD, and I'm sure you have seen many posters and some talks in this conference which present implementations of Measurement Device Independent scheme. In this scheme, Alice and Bob each have a photon source where they randomly prepare a quantum state. Each sends a randomly prepared photon to a middle station called Charlie. Charlie performs a Bell state measurement, publicly announces the result of the Bell state measurement, and from the announcement of the Bell state measurement result, Alice and Bob know what type of correlation they have between them. They can extract the key or make other type of secure communication from those correlations. Notice that in this scheme, Alice and Bob do not contain any single photon detectors, only the sources. And the single photon detectors are in Charlie. But Charlie, you don't have to trust. You can literally go and buy Charlie from North Korea. And if they can make a good Charlie, that's another question. But you literally can buy this piece of equipment from your enemy, because no matter what it does, if it doesn't do the right thing, your protocol does not work. So all the vulnerabilities of single photon detectors by the invention of the FDI-QKD by Hoek-Wong-Lo and co-workers, all the vulnerabilities of single photon detectors have been exported to North Korea. But the problem with this scheme is that it is more complicated to implement than prepare and measure QKD. It is possible. So we have seen many implementations, including implementations over a long distance, over 300 kilometers. But it is more complicated. You have to have better lasers, and you have to have 3 stations, and it is trickier, and it doesn't have the same performance in terms of the bit rate as prepare and measure QKD. So many developers and manufacturers still try to secure the normal prepare and measure QKD against detector problems. And I can just mention that there have been many proposals, and one of the countermeasures, non-MDI QKD, not MDI QKD countermeasure, has been implemented by Quantic. And so this attack on detectors, the blinding attack, has been told to manufacturers about in the year 2009, and in 2008 it was published openly. So Quantic tried to implement a countermeasure in detectors, and they made some tricks inside the detectors to monitor the detector performance. And I unfortunately can tell you that if you follow this publication, you can see that we tested this countermeasure, and even though they tried their best, we unfortunately found a workaround, and we could still make an attack that works around this countermeasure. I don't have time to show you details of this work, but you could see it on the poster yesterday, by the way. But just be aware that engineering implementations of countermeasures are not straightforward in detector vulnerabilities, even though I think it should be still possible. So, I think in the coming years, we will have implementation and certification standards that allow us to make hack-proof QKD equipment. And what is then left for Eve? Will this be the end of the story? The equipment is certified and characterized and shipped and installed with the customer. And it will be secure. Can Eve break it at that point? Can Eve make intentional changes in the cryptographic equipment after it has been installed? Just go and change the characteristics of components to open a new loophole. Can she do it? In a classical communication equipment, this is pretty much impossible because the communication line, nobody has access to the cryptographic module. The communication line is very well isolated from the cryptographic module. But remember that in today's quantum technologies, we have this funny situation that the optical line goes straight to the security critical components. So what we have shown, what has been shown, is that Eve can use laser damage, take a high power laser, several watt laser, shine it inside the cryptographic module and make physical damage, literally melt the components. And there are two examples. So this is one security critical component, a pinhole spatial filter that has been melted and enlarged. And this is a monitoring detector that has been killed by a high power laser inside the crypto scheme during operation. But I will not tell you about those experiments. Attend the last session, the last regular talk of this conference on Friday, just before the hot topics, and Shihan Sajed will tell you about implementation of those laser damage experiments. And in a sense, I think this can be the ultimate attack on the security because it breaks your assumptions by making changes in the scheme after the scheme has been installed and certified. So we have to have some countermeasures against the laser damage. General remarks. So do you think that with all those attacks in our arsenal, we can go and eavesdrop on communication protected by QKD today? Do you think we can do it? Clearly, some attacks will work on QKD, but the actual implementations of QKD do not only rely on QKD. So the cryptographic agreement that you can buy, at least buy from ID Quantic, maybe from other companies as well, implements QKD for key distribution. But it also implements classical key distribution, some form of classical key distribution. Then it XORs the keys, the key from QKD with the classical obtained key by using one-time path or XOR to obtain the master key. And this master key is then used in symmetric cipher to actually encrypt communication. This master key is at least as strong as the strongest of the two keys. So, if QKD fails for a moment, your communication is still protected by the classical key distribution method. And when the classical key distribution method fails, QKD holds. So you need to break both at the same time to break this master key, which I think makes sense. Another important setting to understand is that we have to protect quantum information in the situation that the attacker knows everything, what is inside Alice's and both boxes. The attacker knows all the characteristics, all the component parameters inside Alice's and both boxes, and the attacker can use any future technology, including full-scale quantum computing, to attack on the communication line. And QKD has to protect against attacks in this situation. And the fact that we have to assume that attacker knows about Alice's box parameters is a very well-established principle called Kerckhoffs's principle. In the original formulation, the principle states, it should not inconvenience the communicating parties if the communication equipment falls into the hands of the enemy, and the enemy learns everything what is inside the communication equipment. Another copy of communication equipment should still protect the communication. And we have to follow this principle. Many publications on quantum hacking assume that imperfections of equipment inside Alice and Bob are known, characteristics are known, and they model possible attacks using future technology, like lossless lines, perfect photon number resolving measurement, quantum computing. So there are many publications that say, yes, you can break QKD using known imperfections using future technology. Likewise, many publications model attacks using today's technology, realistic technology. Components you can buy today theoretically model attacks, and publications measure characteristics of Alice and Bob, experimentally measure imperfections in Alice and Bob and model attacks. Many papers about this. There is only one study that I know of which in this situation actually implements the complete attack using today's technology. And in this study, the characteristics of Alice and Bob have been measured by the experimenters having physical access to Alice's and Bob's equipment. So they literally connected measurement equipment, characterized Alice's and Bob's equipment, and then they performed the attack with the eavesdropping equipment tailored to the characteristics, tailored to the imperfections. In the actual situation, when you actually have to go and eavesdrop on the installed line, you will have to deal with the situation that you both have to use today's technology to implement the attack, and you will have no physical access to Alice's and Bob's equipment. No physical access for measurements. And this has not been implemented yet. I think this is doable, but it's quite a bit of just technological complication. And in this situation, what if I think could in practice do, she could buy a copy of Alice's and Bob's equipment, just pretend she's a customer and get another copy. She can rehearse her attack in the setting, she can open the equipment, make measurements, rehearse the attack, make the attack work on her copy of equipment, and then take the eavesdropping equipment on an installed line where there will be another copy of equipment, the copy to which she doesn't have physical access. But many of the attacks, so she will not know instantly the exact values of parameters, which can be slightly different from the copy on which she has rehearsed. But I think many of the imperfections shown today are robust enough so she can make the rehearsed attack also work on unknown copy of equipment, as long as it's the same type of equipment as she has tested. So I think this is doable. It's going to cost some money, but we'll see. This community will probably ask, what about the ultimate secure scheme, the device-independent QKD scheme? In device-independent QKD scheme, the security is supposed to be based on just observed correlations between the measurement outputs. So in this type of scheme, an internal photon source sends one internal photon to Alice, another to Bob, and Alice and Bob use some uncharacterized equipment to measure each own photon. And the security is derived from observing the correlations between the measurement results. So in essence, device-independent QKD is a loophole-free bell testing. So if you observe certain violations of inequalities between the correlations, measurement results, and you observe them often enough, you know your communication is secure. In this scheme, you're supposed not to care what's inside Alice and Bob, because if the equipment does not behave correctly, you will not have the correlations. So can you buy those boxes from your adversary? Actually not. There are still a few assumptions about those boxes. One assumption in the cryptographic setting is that the box does not communicate the detection results through a side channel. So if the box has a transmitter and communicates the measurement results away to it, the security is broken. So you have to trust, even though you don't need to know exact characteristics of the box, you have to trust that the box does not have information leakage channel, intentionally implemented attacks. And also you have to trust that the box does not have maliciously implemented memory, because one type of leakage channel, it can leak results of one QKD session in subsequent QKD sessions by making small adjustments to the report of measurement results. So even a memory, certain type of memory, can break security in device-independent QKD scenario. So it is not a zero assumption scheme. It still has a few assumptions. And just to give you a hypothetical example how the scheme can be implemented and securely. It's a hypothetical example. We don't have implementations yet. But what if there are single photon detectors used in the scheme? And the single photon detectors are now, some types, emit a flash of light when they detect a photon. And this backflash emission can be a leakage channel. So the poster was yesterday about this. And then Bob will have to protect against the leakage by inserting isolators. But then this is no longer device-independent scheme because you are relying on the properties of components. And this hypothetical example shows that even in device-independent scheme, there are still a few assumptions, and you still need to watch what's inside the scheme. So in conclusion, our current rudimentary cryptographic technology is challenging for secure implementation of QPD schemes. But we have very good promise, and research challenges are good. If you want to learn more about practical attacks and practical imperfections, there are a couple of review papers you can check. Yes, and hope you enjoy the reading, have enjoyed the lecture. And I have to give you advertisement. So at present, there is no good review that tells you about everything. And we don't yet have a complete certification standard that you can read and follow all the items, all the steps in the standard and get a secure communication system. So you have to rely on expert advice today to test the security of communication. And my research group has decided to offer such expert advice. So we can work with your industrial implementation of QPD or any other communication protocol and make informal evaluation of its security. So we have to sign an NDA, we have to get complete access to documentation, and I will bring you my students. We will together make a brainstorming on your engineering documentation, talk with your people, find out how your QKD system is constructed, and then we will try to analyze all possible implementation loopholes in your implementation. In particular, we try to make analysis of we will try to find all possible implementation loopholes in optics, analog electronics, drivers, and calibration algorithms, and the operation cycle of the hardware part, the optical hardware. According to our best knowledge, according to the present published knowledge, we will make you a complete, exhaustive list of what is in principle possible, what are possible problems. We will not make complete analysis of the classical post-processing because my group does not have the exact expertise for this, but for those layers, we will try to make a complete report. Here you can see an example, an extract, or to get you a feeling what a developer will get from my group. You will get a detailed list of possible implementation problems with a name of the problem, which components are affected, the description of the problem, and what we will advise, what we will need to complete the analysis to confirm or deny, exclude the existence of the problem, so what additional documentation or experimental testing will be needed. And we will also rank the potential security problems in order of importance based on how likely we think the problem is exploitable and whether it can use today's technology. And the actual report you get is, of course, much longer. So if you are interested, come and talk to me or my students. Thank you, and questions?
Thank you, Vadim, for this nice tutorial. I think we have time for just one fast question before coffee break.
Well, thank you for the very nice tutorial, Vadim. I had a question about the device independent. Maybe I'm confused about something, but you mentioned that you have to guard against information leakage. Now, if everything's in a loophole-free configuration, then are you talking about like a memory attack where if an eavesdropper gains knowledge about all the previous settings, then they can start biasing settings by changing? Because there's analysis protocols that guard against that now. where you don't have to make any assumptions about each trial being independent and identical?
Well, I'm talking about the memory attack based on this publication, and I think it shows that if Alice and Bob have classical memory of the measurement outcomes, then they can leak the content of this memory through many subsequent QKD sessions. So they will make small adjustments to the measurement results, kind of steganography, hidden encoding. And
I think-
yeah, so they will be able, because Alice and Bob do some communication and they use the subsequent results. And then they can export the content of this memory. As far as I understand this paper, so they can export through the many subsequent sessions, they can leak the content. So they don't need a physical communication channel. They can use the normal communication channel they use in Alice and Bob to leak the information.
I think there might be ways to guard against that now. Just in the...
Maybe I'm wrong, so we can talk later.
Okay.
Okay, we're running out of time, so thank you, Vadim, for your interesting talk, and see you at 10:50.